As mentioned in the last video, in a neuron, action potentials cannot increase in size based off of increasing the size of the stimulus. This is in a neuron. Action potentials cannot increase in size. If there was a greater stimulus, what would happen is there would be more action potentials. So there would be a higher frequency of action potentials. However, in a nerve, a higher stimulus can increase the amplification of action potentials. And that is because a higher stimulus will increase the number of depolarized axons. So more neurons would be stimulated here, and that would increase the amplitude of an action potential. So in a nerve, action potentials can be increased because it would impact more neurons, more axons, than with a smaller stimulus. Also, it can impact the intensity by increasing the frequency, just like before. So let's do a recap about this membrane potential change during an action potential. Remember that if there was enough of a change from -70 to about -55, -55 millivolts is a threshold, and if it reaches that, the voltage-gated sodium channels will open. And what this does, remember that sodium is greater, the concentration is greater on the outside of the cell than inside. Sodium is going to rush inside the cell, and that is going to make our cell more positive. And it may reach all the way up to +30 or close to that. And at that point, those voltage-gated sodium channels get inactivated. And remember, it was drawn as like a ball and chain sort of example. I think it's on the next slide. And what happens is that ball comes in and inactivates it. So it's not even closed, it's completely inactive. It's not able to work. However, there is outflux of potassium. Potassium channels are open here. And remember, our cells were high in potassium. It is going to rush out, making our cells more negative again. This upward motion is called depolarization. This is called repolarization because it's getting more polar again. And this is going to even go past our resting membrane potential, down to maybe even -90 millivolts. And this is called hyperpolarization. So it's important to review this because we're going to talk about some refractory periods where when action potentials will not be able to occur. When our sodium channels are inactivated, another action potential cannot occur. So even if you had the biggest stimulus ever during this time, this would not be able to cause an action potential to occur here. Like say you started it right here, because those sodium potassium channels are inactivated, like drawn here. So this is considered the absolute refractory period because no action potential can occur here no matter what. The sodium channels are inactivated. They reset themselves when it reaches -70 millivolts, but the millivoltage of the cell goes below -70, so it gets more negative. This is called the relative refractory period. So it's not impossible for another action potential to occur here. It's just harder because the cell is hyperpolar. The cell is more polar than it would used to be. It needs to go further from -90 to -55, right? To hit that threshold. So this is called the relative refractory period. So neurons act like crappy cables. They have some cable properties, and we're going to discuss how they're actually pretty crappy cables. The ability of neurons to conduct charges through their cytoplasm. So they have the ability to gain positive or negative charge through their cytoplasm, as we've been saying. However, there is high leakage. And so there is going to be leakage of positive charges throughout the axon. And so look at this picture here, and what this is showing is here is a electrode stimulating an axon, and it's inputting some positive charges there, and it's inputting enough to raise it to -60 in this spot. And what we see as we move down the axon length is that there is going to be leakage of these positive ions. And so as we move down the axon, the millivoltage of the axon is decreasing steadily. This is what makes it a crappy cable. There's a lot of leakage of these positive ions. This is going to impact the speed of the conduction of an axon. So let's take an unmyelinated axon to begin with. Notice here that an action potential occurs. We have our voltage gated channels. It gets really positive inside the cell. And what happens is it's going to depolarize the areas next to it. And so there's an action potential here, then this place gets repolarized, but this action potential is going to cause the action potential to be regenerated right next to it. So it's kind of like at a baseball game and doing the wave, right? It's kind of like bam, 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 kind of like domino effect down the axon. So action potential, depolarization, this specific area is now repolarizing, and then it is back to its resting potential, and it propagates new action potentials down the line. This has to occur in an unmyelinated axon, and it has to have an action potential occur all the way down the axon length. So conduction is relatively slow. So what can actually change the speed of our is myelin. In the peripheral nervous system, Schwann cells produce myelin that wrap around our axons, and they insulate our axon, and they are going to actually prevent that leakage that we just recently discussed. And so what we find is that there will not be leakage of positive ions where there is myelin. And what we see is that an action potential occurs at the nodes of Ranvier. And then those positive ions during the depolarization, when the sodium channels are open, can actually move through those myelinated areas and trigger an action potential in the next node of Ranvier. And so it's kind of like these action potentials skip from node of Ranvier, and then it leaks. I shouldn't use the word leak. It spreads through node of Ranvier, spreads through node of Ranvier. So it's kind of like it skips, from node to node to node to node. In that way, it increases the speed of conduction by a lot. It's much faster because action potentials are going to skip from node to node to node to node. And what we find is that there are actually only voltage gated sodium channels at the nodes of Ranvier in myelinated axons. And like I said, there is no leakage of these positive ions where there is myelin. This is called saltatory conduction.